First of all, I'd like to welcome everybody to this symposium for newly elected academicians of Academia Sinica. And I welcome, so on behalf of the Institute of Mathematics, Institute of Statistical Sciences, and also Institute of Computer Science, I would like to welcome you to this morning session. So the first speaker this morning is Professor金芳蓉, or Fan-Chung Graham, from University of California in San Diego. So let me say a few words about Professor Chung. So she graduated from National Taiwan University, so she's an alumna of this university here, math department, and then went to University of Pennsylvania, and that's where she got her PhD. And if I'm not mistaken, then she went to work for Bell Labs for several years, probably almost 2 decades. And then afterwards, she returned to academia, where she taught at the University of Pennsylvania. Afterwards, she went to University of California, San Diego, and she's mostly she's well known for her contributions in the spectral graph theory, and this will be also the subject of her talk. So among her many honors, so she is a fellow of the American Academy of Arts and Sciences, and of course she was elected to this Academia Sinica, so she was elected to an academician of the Academia Sinica 2 years ago in 2016. And so the title of our talk today is Geometric Aspects of Spectral Graph Theory. So let's welcome Professor Chung.
I am honored to be here giving this lecture, and 非常高兴看到很多的老朋友、新朋友。What I'll talk about is the geometrical aspects of spectral graph theory, 几何方面的谱图论。我如果翻译的不太好的话，请大家包涵。很多专门名词 I will use both languages. So an old saying in geometry is, can you hear the shape of a drum? 能不能从听到的声音或者是频率来断定它这个几何物体的形状？那当然，我们现在讨论的，在这个 talk 讨论的不是 drum， 而是一个 network. It's network very large size, almost like a drum. So we want to use basic tunes, basic frequencies, 少数的数量来决定呢，来引导出这个 global properties and behavior， 能够把数量来做一个控制的这个它行为的方法。有一个很好的比方，就是这个one of the analogy is a galaxy far, far away. When you have a network so large, you don't want to look at every little places. You want to think of it as some place very large. You can a galaxy far, far away. Okay? So although no one can really be there, however, as early as 18th and 19th century, scientists was able to predict the molecules, what the makeup, the composition of just from the light. And here is a solar spectrum. 从这个光谱来断定它是什么样的分子的结构、元素等等。这个图是这个 C60, Buckminster Fullerene, a newly, relatively young molecule with a beautiful shape, and you can really validate this molecule by looking at its infrared spectrum with relatively few lines. And so what we are talking about is a graph, okay? And it has two main things. It has 点 vertices, and it has edge, which are pairs of vertices. So it's really a relationship. So for example, every web page can be think of as a vertex, okay? 点就是 web page, and 线呢就是 the hyperlinks. 你如果能够从一个 web page 点了，然后到另外一个 web page， 那就是一个 link. 所以这种graphs has all different kinds. It comes from geometry, comes from sort of topological different spaces, comes from edge break type with great symmetry. But in general, it can be any social networks, it can be internet graphs, it could be any information networks, biological networks, for example. So what we want to do is to find basic tunes. For example, eigenvalues, which I'll talk about a little bit more, 特征值, to capture its global properties and behavior. Okay. So here are a few pictures that my student made. So this one is the internet routing graph, sort of very rich, interesting structure. And this is another one by my student, which is the anything related with energy, power grids. And this one is a social network, 是社交网络的一种. So every mathematician is a vertex. And if they write a joint paper, then there is an edge. So one, and also in bioinformatics, biological information networks, disease spreading in a network, as we can see. If any two people with a potential contact, that's the contact graph, and people can talk about disease spread around. So we want to use relatively few quantities, which is what mathematicians always want to do, right? All scientists want to do. Use relatively few quantities and control very complicated, complex object and behavior, like connectivity, diameter, identify bottlenecks, for example. And this picture is a Twitter graph, and it's also a social network. So on one side, probably a lot of us sort of know geometry. Geometry is the three-dimensional Euclidean space we live in, right? And it has various shapes, could be more complicated, and it is continuous. Continuous is it really 连成一片, right? And it's not only continuous, but it's differentiable. It's not only differentiable, it's second-order differentiable, high-order differentiable. It's, even the derivatives are all continuous. So it's a very different object from the other side of the networks, as you can see. And here is versus continuous, it's so-called discrete. And 通常的翻译是离散。可是离散 really doesn't really capture its spirit. Discrete really means 是各自的. So everything 就是0跟1 and no 1.35 square root of 2 or whatever. Okay, you either are friends or you are not friends. Okay, not a semi-friend. Okay, so discrete 现在都用离散。没有一个更合适的这个translation 啊。So 可以看出来几何跟这个物理方面很有关联，在那边有很多好的题目，那这个几何在那里很有用。那在 discrete 这边呢，在 computer science， 现在 network science、data science。非常的就是 mathematical foundation for 这些 areas。那从这些 areas 呢，也是有很多好的问题，所以是一个 two-way street， 彼此都很有好处啊。 我要说的呢是，在几何上面，很长久以来，大家有很多很重要的工具，很重要的工具呢，就是特征值 Eigenvalues， 在图论上面也有 Eigenvalues。如果你看的对的角度，这两个东西其实是互通的。另外一个我要谈的呢是 Curvature， 这个 Curvature 是一个非常 geometrical term， 对不对？曲率，对不对？在这个随便一个social network 上面，怎么样子算是一个几率呢？那这个最近2-3年啊，其实不止2-3年，在这边这个用这个analogy of curvature in geometry, we can derive a version in graph theory, and 非常有用。这两个区域呢，看起来是很不一样的，可是呢，就像数学很多的区域，有很多的不同的科目，代数、几何、拓扑等等啊，微分等等。可是我们都知道，如果你深入一点的话，它其实在根部通通是互相连接，而且呢，就像下围棋一样，所有的领土如果连起来的话，力量就特别的大一点。那这就是我这个 talk the point I want to make. So one side we have geometry, and the other side I would like to give you a flavor to see how it's used in spectral graph theory. And in fact, I remember my co-author, Professor 邱成桐，他就说了，这个如果你去看这个 local behavior 微观，那是完全不一样的。One side is continuous, the other side is nowhere continuous， 对不对？可是你看这个 global behavior 宏观来看的话，有很多的相似的地方。而事实上呢，我在做这一门的时候，我翻开那个 differential geometry 的书，去年要这个组通常用的书，这个定理跟我们写的定理很多都是很像的，可是方法完全不一样。因为在 differential geometry 第一个方向，就第一个用的东西就是 differentiation， 把它放到 zero 去看 maximum point。我们这边没有 differentiation， 所以这个用的工具完全不一样。可是姚又说了一句话，他说，因为在 Discrete 方面是看的是大的方向，所以把这个 global behavior 在 geometry 里头可以看得更清楚。因为这个 discrete 是哪一些的力量是在 global 上面跟 local 分开了，看得出来它的这个区分。那稍微讲一下 graph theory 是大概250年的历史 ，started from Euler， 7桥问题，需要有这个趟呢 Königsberg 有7个桥，需要走一个路线呢，可以把7个桥通通走一遍，不重复。Spectral graph theory 谱图论的历史呢，其实也是算是相当早的，在 graph theory 来说，很早就有跟这个chemical compound 化合物的 connection。比如说这个benzene， 这是有它的这个 structure， 所以他们用特征值呢来算它的这个 stability， 它稳定还是不稳定，是在什么情形下从液体 变成气体等等，这个能量的转换。当然还有buckyball，所以这个是有长久的历史。在比较早的时期呢，比较是 Discrete graph theory， 就是用它来看这个很漂亮的图。那这个 Spectral 很少的线，然后这个 Expander graph 在60communication networks 有很多的 applications。这个 Spectral graph theory 我用几何多了一点是在 1990s， 我那个时候在 Harvard take a sabbatical， 碰到秋天开始用这个 spectral geometry 的ideas 来to do spectral graph theory。最近些年来it breaks spectral graph theory really in full force。他们 really come along the way. So spectral graph theory is a spectrum of a graph， 一个图的谱。One way to think of it is a discrete Fourier transform. And we sort of know Fourier transform. We were taught in the book or in class. Usually it goes like this, okay? Only after many years later, I started to realize, see, usually the definition it hit you with, oh, it's periodic. Then you hit you with pi and e and I all at once in the expression. So that's the definition, sort of going through a black box, and you are handed this expression with integration and pi and e and I all at once. Okay. So only after many years later, I started to understand what it really means when I do discrete. So another version is something like that. Under some complicated condition, you are handed this Fourier transform. So the way I see it is that suppose you have cycles, so A goes to B, B goes to C, and so on, and you put out an adjacency matrix. If they are adjacent, then you put a 1 there, okay? So this is sort of a cyclic matrix. So it has nice eigenvectors. So what the eigenvectors mean is that you just solve the equation, right? The A times Y happens to be lambda times Y. So mathematical point of view is really say, you just solve these equations. From physics and other point of view, it's equilibrium. This lambda shows the energy. And from computational point of view, this is really a matrix. It's a complicated thing. It's describing how things are moving in the universe, right? The rules of matrix multiplication is complicated. However, you want to make it easy. You want to multiplication like a number, lambda. Lambda is a complex number. So you want to make it as easy as usual multiplication. So that's the spirit of Fourier transform, really. So here you take, this matrix is very special. It's a cyclic matrix. So you take nth root of unity, call it theta. You can write theta more careful in that form. You see your pi and theta coming out. And you get sine and cosines and these angles. And you can see all the Fourier transform with all these sine and cosine curves, right? That's where they are coming from. And so you are giving any vector, okay? So every vertex, so every coordinate getting a value. So what are you going to do? You are going to express in the basis in terms of eigenvectors. Once you express it in terms of eigenvectors, then the multiplication just raised to eigenvalue, raised to the kth power, right? So the multiplication of matrix is just like using numeric numbers. And so why is the Fourier transform? Fourier transform is that you put it into such a good basis. Those coefficients are the Fourier transform. So if we compare with the classical, compare with the usual transform, you can see it's the same. Just replace integration by summation. You explain E and pi and I, right? Or it is just the consequence of a cyclic matrix. And all these conditions are complicated conditions, periodic, whatever. Those are really not so important. It's just for compactness. So you can write such a thing. So, however, we don't just have sine and cosine and these curves, because we have n cubed for the information, 0, 1 strings live in this universe of n cubed. And so this is one-dimensional, two-dimensional, these pair-dimensional cubes. And for these cubes, you can see, you can put it a Hamming labels there. Distance, Hamming distance 1 is the edge, right? And for the n cube, the transform is very different. You don't get sine and cosine. They're pretty. They are 1s and -1s, and you scale it up. It's a different universe, different transform, different bases. And that's not the only one, right? The Cayley graph, I always love to use the buckyball as the example, which is easy to describe. The vertices are described by a group because you have this rotational symmetry, right? Vertex transitive, the polymorphism among the vertices. And you have an edge generating set. In our case, the vertices are labeled by the even permutation group, A5, the alternating group. And the edges are just these 3 elements, the permutation written in cyclic form and in cycle form. So that's the labels there. So that's the truncated that's the buckyball. And when you have symmetry, what do you really want to do? It is something you always want to do with a matrix. You want to break it into smaller pieces. And then in group representation, it's called irreducible representation because you want to break it into small parts. Diagonalize, if you hope you could. But in general, if it comes from groups, then group representation gives you the irreducible representation. That's our friends in algebra work very hard all the time for us to use. We are very lucky. And so the buckyball, the vibrational spectrum, just compute from the irreducible representation of A5. So for spectral graph theory, so it's really just generalized discrete transform. Okay? So instead of all these waves, what happened? We are going to have the past and also high-dimensional Euclidean space, the high-dimensional grid, are these sine cosine curves, some combinations of that. But we also have trees. We have cubes and subgraphs of the cubes, and we have any arbitrary social networks. We have all the whole transform. So it's much more general. Okay, so let me get out of here. Okay, so here is a sort of an outline. I'm going to talk about eigenvalue, how we derive the right eigenvalue, put it in the right framework so we can associate with spectral geometry's eigenvalue methods. And immediately you can see the geometrical flavor. Because once you have eigenvalues, you put down all the eigenvalues down in the real line. In our case, our graph is symmetric, so the matrices are symmetric, so I need to get real values. So there are gaps in between eigenvalues, and they have their meanings. In fact, that's the whole expander graphs and all that was about. But I'm mostly going to talk about stretches in eigenfunctions. Because when you have eigenfunctions, then you think about you have a graph. All the edges is like rubber band. or some elastic 弹簧. Okay, so once you have eigenfunctions, eigenvector 特征向量, you sort of nail them down. So all the edges like elastic band got stretched. How much they are stretched? Can we say something about it? So that is actually has a lot to do with eigenvalues and with curvature of graphs, which I'm going to describe. So if we get through that, then we can talk about mysteries and problems. You guys have enough. So we have eigenvalues on a line there, and here is one gap, right? And we have a graph there. You can see usually it is just vertices and edges. It doesn't matter how you put them down. It is the graph we mean is just the relationship. When you put it down, then it's a geometrical graph. But you don't put them down arbitrarily. We want to use some good way to put them down. One way to put them down is to use eigenfunction. And in fact, that was the main idea of spectral algorithm. That is one way that you nail down your position of your vertices, so you hopefully can find your clusters better. Okay. So first we talk about how to derive our eigenvalues. There are many ways to derive eigenvalues. And the usual way is to the adjacency matrix I show you. To put 1 or 0 if there's a link or not. Okay. When you label all the columns and rows by the vertices. So we want to find the way to define the matrices so that the eigenvalues you get out of it have good meanings that you can really use, right? To relate it to things we want to capture. So previously, it's the neighborhood expansion and all that. I think when I was taking a sabbatical and spent my time in Taida, I was covering quite a bit of that area. So today I want to talk more about curvature. So there are adjacency matrix, and also Kirchhoff has the material Laplacian, which comes out from electrical network theory. And but I'm going to use normalized Laplacian because one reason is the really control diffusion, control random walks. And it's actually the right way to do it. So the one way to think about it is the discrete Laplace operator. So you have f is, think about it as a vector with all the entries labeled by vertices. So every vertex getting a value, so that's f, okay? You want to delta f, the operator acting on f, is the average of the degree. So how many neighbors coming out of x is dx. And you're summing over all the neighbor y, fx minus fy. So one way to think of it is think about the case of a path. So when you have a path, so you have one node after another. So you label, okay, I should put f delta fxj. I forgot the subscript j there. Okay. So what if I only have two neighbors, right? The neighbor j plus 1 and j minus 1 for xj. Then you can partition that sum into two differences and take difference. So that's the analogy for the second, and because the classical Laplace operator is the second order derivative, right? So you can see when the graph is a path, it's sort of, you see the correspondence there. But now if I have social network, then I could have many neighbors, but still we have a valid definition there. So the normalized Laplacian, see that if I put the discrete Laplace operator into a matrix form, so I have matrix times a vector, so matrix formulation, that matrix is not symmetric. It's not symmetric caused a world of problem. The problem is that if a matrix is not symmetric, you might have complex eigenvalues.
What is dx?
Dx is the degree of a vertex. How many neighbors you have?
How many edges?
How many edges coming out? So, so one way we need to do is to symmetrize it, so you don't have to remember multiplication from the left or multiplication from the right. The symmetrized version is the normalized Laplacians. So one way to symmetrize it, you get square root of dx dy. And that was the reason my friends in combinatorics at the beginning have great resistance. No one likes square root of dx dy. They like 0 and 1. And I don't blame them, okay? But from the very beginning, I realized there's no way to get it wrong. You have to do it this way. If you don't do this way, you just use adjacency matrix, then the spectral gap doesn't corresponding to diffusion, doesn't correspond to bottleneck, doesn't have all the good geometrical meanings. So only after a few years, people in other areas started to pick up. People in vision, computer vision, in optimization, they started to use it. And then, computer science, they need it. They really, because even if your universe is very beautiful, see, if the degree is a constant, it's a regular graph, then it's only different by scaling. It doesn't matter so much. But most of the graph, the information network is very uneven, so it's not regular at all. So when you deal about any problem there, so in computer science, full force, you have to use this. So I think now people in graph theory finally came around. So, and another very nice thing about this is that after this normalization, the eigenvalues all put in the same framework. So previously, if for adjacency matrix, if the degree is big, then of course the eigenvalue will be much bigger range, right? And now if you do the normalization, all the eigenvalues will be 0, 2, which is very good, because then you started to have something you can compare to graphs. You want to know which network will live, which one will die, which one's better, if you are making improvement quantitatively and numerically. And once the spectrum all are in the same framework, then there's a possibility of comparing them, especially when we are talking about the first non-trivial eigenvalue, which is the spectral gap. And immediately you get a lot of property out of it. You can see how many connected pieces you get, how many connected components you get, some structure coming out, and you also get the relationship with the diameter, which is the furthest distance between any 2 points. And so I want to talk about stretches in eigenfunctions and the curvature of graphs in the remaining time. So what is the curvature of a graph? So in geometry, it's a very common concept. So this is very, very vague definition, and I understand. So if they are geometry here, I apologize. It's basically a quantity, it's a measure that when you have a surface how different it is from the flat plane. Okay, so you take the tangent, you see the ball there, and so on. That's one way to define curvature. So what happened when we have a graph? We don't have a Euclidean plane there. We have a bunch of nodes linked by some wires as a abstract body. Those points can, up to you where to put them, right? So that's the, what is the curvature there? So one way to give a definition, the best way is to see where you really want to go. If your definition is really useful, if it is good for something, okay. Especially I'm talking about this because it happens to be many different definitions of curvature. So the way I'm going to define it is, I hope it is at least one way that I see it, you will say, good, this is a reasonable way to give this definition. So what we want to say, suppose your f is eigenfunction. If you are talking about its arbitrary function, it's a discrete function, I can assign any values, it doesn't make any meaning, okay? But suppose it's a very nice function coming out from, a very good assignment coming out from eigenvector, 特征向量, okay? Then I want to say if these two are neighbors of each other, they are linked by a link, so there is a 弹簧 in between, okay? So they should be close by. They should have some notion of smooth. So we want to establish such inequality. So if you look at eigenvalue, so usually it is, Schmidt form. So it is this Laplace operator particularly nice. You can write it as a sum square. On the top and at the bottom is also a sum of square, which is a norm. But we take the degree into consideration. So the difference of 2 points, what should I compare with? I should really compare with its length, right? So that's the same way as how I write. So as you can see, the normalization. See, if I don't have dz there, that's the consequence of taking adjacency matrix. But especially in social network, you have big degree and small degree. In theory, you can take any measure you like for graph. But the idea is choose a good measure, so you'll make geometrical sense, right? So here, if I choose it to be degree, see, they sort of line up nicely, so that I know how to compare with. And I'm talking about second eigenvector because the first eigenvector is a constant everywhere, right? So you have orthogonal to the all constant vector. So the second, it is the eigenvector associated with the first non-trivial eigenvalue. So that's why this orthogonality condition. Okay. So this is sort of a heavy slide, which you don't have to really look very far. So what I really want to say is that, okay, I want to bound it. I want to bound it something like using eigenvalue. Actually, in one of my previous graph, I talked about the spectral gap is less than 1. So it's in many situations, it's a small quantity, okay? So we want to use eigenvalue to upper bound it, if possible, and make the max to be 1, okay? And so we start looking at this problem. At first, we look at homogeneous graphs. So there are many terms here, which you don't have to. I'm not going to give you all the definition all at once, but please give me a little bit room to place it there first. Okay. So for these very nice graphs, we define the notion of Ricci flow. And then the curvature comes in. Also, if you have a control of both eigenvalues and curvatures, you can start it to bound this rubber band stretch at the edges in eigenfunctions, stretched by eigenfunctions. And suppose we walk away from these very nice homogeneous graphs to general graphs, you can still do it, depending on how you define it a little more. And there's so-called strong harmonic inequality. What does that mean? It means if your point is close to maximum point, remember we say the maximum point is 1. When you are close to maximum point, the stretch is even tighter. That's really a discrete analog of the Li-Yao, those inequalities. So homogeneous graph is just you can use a group to label the vertices, or use quotient group of a group to label the vertices. Then we call it homogeneous group. So another way to say it is that all your edges have very nice labels. They are generated by edge labeling set. And one way to think about this edge generating set is that for every vertex there are directions. So your geometry started to form. It's like you have a zone, x zone, y zone, z zone. You have a frame there. So before we plunge into anything, I want to convince you that this notion that you can bound adjacent vertices is a good one, in the sense that I can immediately suppose your function, two neighbors in your function are upper bounded, then you can get a relation with diameter immediately. You can get some eigenvalue lower bound in terms of diameter. And this is actually quite important because, for example, for a lot of real-world graph or random graph or expanded graph or most of the graph you see, the diameter is like log n. Because small world phenomenon is another way to talk about the diameter is relatively small. And usually it could be the lambda could immediately get a pretty nice lower bound. In many cases, it's close to best possible. Okay? And you can see as soon as you can control the stretches, then the diameter started to pop up. It's actually almost a one-line proof. So this notion of adjacent points are controlled by eigenvalue, which is sort of an analytic condition, versus the diameter is small. That's an arithmetic kind of property, but they are related. So well, that is what gets mathematicians excited, I guess. Okay. Now I'm going to say getting closer to defining Ricci curvature, right? So Ricci curvature, as you will see, it's a local property. So for every node, I only check up to second neighbors. So it's a local property, but somehow it has a global behavior. What is a global behavior? Is to say any point in the eigenfunction should be close by. That's global behavior. That's a very strong conclusion based on local property. So before I define it, I want to say, okay. I think I forgot about something. I don't want to plunge into this too fast. Okay. I think this is still okay. I want to first tell you about what Ricci flat is. Because if we're talking about curvature, we have to talk about flat first. Flat is the situation your curvature is 0, okay? So how will I get the Ricci flat definition, okay? So here we have some notation. See, in early days when I was working on this, I really write out all the summation sign very carefully because the integration sign is very beautiful, but usually integration sign omitted a lot of things. You usually have integration over a manifold. So, but for us, for a graph, you have vertices and edges. They are all very different sums. And but now it has been 15, 20 years almost. So I started to use the more borrow the nice definition for spectral geometry and hopefully it doesn't induce confusion. Okay, so you have gradient, right, and you have Laplace, and I can replace the summation by integration sign, which is a beautiful symbol. It is, I think, for physicists commit the most sin, because when they write integration, they really don't specify where you integrate over. But for discrete mathematician, if you are wrong even one index, then your hands is in the cookie jar being caught. It cannot be off even a little bit. The limit won't save you. Okay. But that's the nice part of being discrete. It's totally clear, easy to check. So we want to prove this. Okay. So usually in spectral geometry you use variation principle. What does that mean? You take a maximum point and you started to say, if the maximum point is bounded, then you bound everything else, right? So there's one more condition there. So you have your first derivative, second derivative, and everything there, right? At your disposal. You want to say at the maximum point, if I move a little bit, it cannot be more. That's the variational principle. Really very simple, like pigeonhole principle. But in discrete, we don't have derivatives, but we have inequalities. So that's what we are going to use. So I'm not going to bother you with the proof. I only want to say how the concept coming out. So I want to say it is small, so the sum should be small. So I'm going to look at the Laplace. So I'm looking at the maximum point and how it differs from its neighbors, right? So you expand it up and cross a few not important terms, and you ended up with a lot of stuff. And you want to clean it up. How will you clean it up? If you kill a term, then you are going to get a beautiful expression. That is the Ricci flat. That term disappears. So if it disappears, then I have a beautiful form. I can play around a little bit, usual trick and whatever, and then I'm going to get that. So that's Ricci. So what it really means? It means for any fixed A, so in direction A, you have two ways of second order neighborhood. You can walk, take an A, and then walk to all the possible B's. Or go to all possible B means go to all neighbors, and then take a direction A. And Ricci flat say those two sets are the same thing. So it's a second order behavior, second order neighbor behavior. So that's the story, okay? So if your homogeneous graph, if it's commutative, A, B can interchange, then immediately it vanishes, right? So x is going to, in direction A, you go to AX, which are the two group operation multiplying, okay? And then you go to ABX equal to BAX. So if it's abelian, it's immediately flat. So we are getting tons of examples for Ricci flat graphs right there. But you could be a little bit different, okay? So you have go in the direction A and then go to all neighbors, or go to all neighbors and then go to direction A. And the Ricci flat, it says for any fixed direction A, these two kinds of second order neighborhood coincide. So that's the Ricci flat. And that's exactly what the proof was telling us. Okay? So that's the Ricci flat definition. So how about when it's not zero, okay, not flat? Many different definition, Olivier definition, so using so-called transportation distance, which means really you have a distribution and you have another distribution. How do you move this distribution to the other distribution in the fastest possible way? Sort of like a route going over. So that's the transportation distance. So basically, you move one, so there is some definition there, okay? And some people use that one. And there's a Bakery-Emery definition of Ricci flat, which is more complicated. It says for all functions, you take this gamma function, and so on and so forth, and then it satisfies this condition for all functions. For all functions is a problem for us because discrete, the function could be really wild. You don't have continuous, you don't have other, you don't control that, okay. So you can see a lot of things. So what we really want there, so Bakery-Emery, if you see through all the definitions, all those table, you know, if those equations sort of killed all the intuition, which is the beautiful part of geometry, is the intuition play a big role. So Bakery-Emery really says that for all functions, this is small. This is my interpretation. For people really using those equations, they might not agree with me. Okay, but you can see for all functions, it really is a too tough a condition for us to do. So I'm going to really say that for general graph, what do I define the Ricci curvature? First, I will try to put a frame on. I'm going to organize all my neighbors in some way, so they all have the same measure, and then they have some direction, and which is not very far from computer scientists trying to do. Their edges all have labels. They care a lot about which one to go to, which neighbor to go to first. So so here's some definition of putting out a frame, okay? And the frame is the usual definition. You think the frames should be, okay? And then really two definitions of Ricci curvature. So one thing is that only for eigenfunction, this term should be nicely bounded, like this kappa. But getting eigenfunction is not an easy thing from a graph because it means going through a linear program and solving equations, okay, eigenfunctions, right? So the second definition is, which is actually my preferred definition, is to say that for every node in every direction A, these two kinds of neighbors are not so far away. So what is not so far away? If I measure in transportation distance, they are not so far. So that was one. These are two distributions. Once you put in frames, so there are two distributions. How they are not so far away. If they are identical, the distance is 0, then you get Ricci. And with this notion in mind, we can do everything. So you can more or less see how the proof goes. There's no other way to do this. Okay. Then I have one notion is closer to the Bakery definition, and the second one is just use the flow definition, and have a little bit Lipschitz condition. And with this, we can do this third line for general graphs with bounded rich curvature, then we can get something. And I won't just say a word about strong hardening inequality. I guess I better rush, but I think the strong hardening inequality says when you are close to maximum, you are gaining. Your eigenfunction pull them even tighter over there. And and this is the example, right? When you have a cycle, you see near the maximum point, it is much smaller. Very much tighter there. And which in the spectral geometry proof is actually the trick is finding the right function to consider. But in the spectral geometry, usually there has these logs and so on. But somehow, this actually took a few years that we found a good potential function there to maximize. But once you are that, then it falls out. And I just want to use the remaining, my time is almost up. I just want to mention one problem. So that's, I call it mysteries. So this is an old newspaper saying that in New York Street, if you close the 42nd Avenue street, so somehow the traffic got better. So what happened? You kill an edge, the graph got better. So very counterintuitive. But first of all, we have to say, what does it mean your graph got better? So I'm going to use very definitive definition chosen by this measure, it's a spectral gap. The bigger the spectral gap, the better. Which is actually a reasonable thing to use, okay? So which means the diffusion is better. Okay, is there an edge so that you kill an edge, it has a larger spectral gap? So that's the spectral question. So we went around to do that. We take a random graph. You call it red if you kill it and the graph get a bigger spectral gap. Otherwise, you color it blue. So my student be busy drawing pictures. For every edge, they have to run an eigenvalue problem. And indeed, there are a lot of edges should be killed, it turns out. Amazingly large number. Like more than 40%. And that happened a lot of the times. And so that's here's the conjecture, which is over. So it has a random graph model, but because causing every edge with probability independently with probability. Okay? And in fact, I think that constant is a half. I think 40% just because we didn't do such a big problem. I think with this, I'm going to end this talk. Thank you all very much for listening.